And the title of today's talk is The Beauty of Living Together, Social Insects. Let's get started. So before I go over my presentation today, I want to introduce myself very quickly. As I said, I'm a new urban IPM advisor in Capital Corridor area, and basically I'm focusing on insects that bug you at home. So we call those insects as structure pests. Those structure pests include cockroaches, ants, termites, bedbugs, and that you may have seen at home, or maybe in the future you will see them at home. So at UCANR, I provide extension program about urban pest management, and I do my own research about the biology and pest management of urban pests. So if anything's bugged you at home, please reach me out. I can discuss with you about your future treatment plan or what you can do. So among many structure pests or urban pests, some of them are social insects. That's what I love to study, and I have been studying social insects for about almost 10 years now. So today I will talk about some biology of social insects, and I hope you enjoy. So who are the social insects? Can anybody type in the chat? Who are social insects? That's correct. Bees, ants, that's right. So if you ask same questions to introductory entomology students, they would say ants, termites, some bees, and some wasps. We call those insects as eusocial insects, but commonly we say just social insects. And all eusocial insects have three different characteristics, and I will go over this characteristic in the following slide. So here you see leaf-cutting ants, and this is termite from Brazil, Amazon area, and honeybee and wasps. So compared to other, insects overall, they are very successful creature or organism in terrestrial ecosystem, but social insects are very successful organism in Earth. So if you look at biomass of livestock, human, wild terrestrial vertebrates, termite, ants, and all other terrestrial arthropods, the biomass of termite and ants exceed humans' biomass and livestock's biomass, or the total insects biomass. So they are very successful. So what makes them very successful is because a social behavior. So social behavior can be defined, broadly as the presence of cooperation and some form of organization, whereby the action of individuals are coincident and coordinate or communicative in some ways. So today I will go over what they do. And as I said, all eusocial insect or social insect display three characteristics. So the first one is reproductive division of labor, meaning that there is an individual that solely focuses on reproductions. And the second characteristic is overlapping generation. So in social insect colony, there are a number of different generations living together in a colony. And the last characteristic of social insects is cooperative brood care. So everybody chip in brood care, like human beings. Okay. So here is an example of reproductive division of labor. This is a termite queen, we believe this queen's age is about like 20 years old, and she is very chubby, and she lay about 3,000 eggs per day. So basically, termite queen is egg laying machine. So, or you can find this kind of reproductives in social insect colony. So I said reproductive division of labor, but there is another form of division of labor in a social insect colony. We just say division of labor. So for example, in our home, we have mom, dad, and kids, right? And we all do different things. Like for example, mom and dad go out and they make money to support their family. And mom and dad, I mean, all family can go grocery, but usually mom and dad go grocery shopping and they make food and they feed their children. So in our home, kids basically they are chill and they do what they want. So on the other hand, if you look at a colony of social insect, this is termite example, and queen and king focus on only reproductions. And worker is basically kids in our home. They do most of work for the colony, like brood care, nest maintenance, and food finding and food consumption. And there is another special caste in a social insect colony that is soldier. So this caste is dedicated to defend their colony against intruder or predator. So if you look at ant colony, in ant colony, like similar to termite colony, there's a queen. Queen is much larger than other castes, and there's a king, and there's a workers. So, and if we look at honeybee colony, we know there is a queen in honeybee colony, and more interestingly, in honeybee colony, individuals do different jobs depending on their age. So, for example, when bee emerge from cocoons, they do cleaning the dirt and in honeycomb first. And then next week, they start feeding larvae. And then after a week, they start building honeycomb and receive food from incoming foragers. And then later on, they do like they remove horse or they become like the hive guard. And then toward the end of their life, they do forage for nectar, pollen, or water. So this is kind of transition of jobs that single bee experience over time. So basic entomology class. So insect sociality terminology. So we have many different like terms to describe sociality in insects. While the term social insect will likely always refer to social groups like honeybee, bees, wasps, termites, and ants, that doesn't mean that they are the only social insects in the world. Other just an interesting form of sociality, like some insects are self-social, communal, quasi-social, semi-social, parasocial, pre-social, and eusocial. So this is quite complicated, but you can understand this concept as a concept like so I explained three different characteristics, right? Of three different characteristics of eusocial insects. So if an insect display only one or two, they are considered like one of these, like self-social to pre-social. Eusocial insects are the only social insects that display all three characteristics. Okay. So I'm not sure if you have heard about phylogenetic trees. That is kind of evolutionary trajectory that insects went through. So in insects, sociality has been observed in at least 14 different insect orders. So sociality has evolved independently many times in insects because pretty good, they are pretty good trait to survive. So um so before social to evolve toward the sociality, there is some precursor which is parental care. So what they mean is that adults, insects perform some degree of parental care, like maternal care or paternal care. So maternal care is somewhat common in insects, and at least 12 different insect orders display maternal care. And this may include offspring protection from environment, parasites, and predators, or food provisioning or grooming, like to remove fungal pathogen. And the good example is true bugs, hemiptera. So they do care their youngs or their younger brood. And maternal care is very common in earwigs, the order Dermaptera. And if you look at these pictures, female earwigs perform egg grooming, and they do protect their offspring, and they do food provisioning. So we can say earwigs are excellent mom. And related to maternal care, paternal care is kind of rare. But male giant water bugs, they perform exclusive paternal care, and this is a great example. So male giant water bugs carry their eggs on their back, and they make sure these eggs are well oxygenated and they they are moist enough. And another like maternal care, relative to maternal care, biparental care, which includes maternal care and paternal care, is also rare. Both the male and female perform some degree of parental care in some beetles, like this best beetle and dung beetle. And another good example of biparental care is found from Cryptocercus wood roaches, which is close relative to termites. And this is a living example of what the ancestor of termite may have been like. So they harbor wood digesting microbes, and they pass this microbe to their brood, and they are dependent to they are dependent on this microbe. So biparental care in Cryptocercus uroch is a form of extended parental care. They do this 3 or more years, like 5 years, and they typically produce only one brood of nymph, and they invest all their resources to their brood. And as I said, adults provide those nymphs with symbionts via protodiotrophallaxis. So here the protodiotrophallaxis is passing microbes or symbionts through from anus to mouth. So this is critical to survive, and the parents must have completed this transition to their young. So also the adult woodroach provide food to their brood, and they defend and sanitize and excavate gallery in the rotting logs to build their house. So and termite is a great example that performs biparental care in insects, and both king and queen are involved in colony foundation and development. Like similar to Uzroach, these termite king and queen have their symbiont, and they have to pass this symbiont to their brood so that those individuals can survive and feed on wood. So as I said, social social behavior in insect is not that common, but social evolution was happen at least like 11 times independently. So now let's go over some fun behavior of some behavior that social insects display. Any questions so far? Jen, do you have any question?
No questions.
Okay. Okay, so let's move to individual sacrifice. So basically many insects are solitary and they have no reason to self-sacrifice. But social insects, they display an individual sacrifice for their family, their colony. So here, globe termites, this is one of termite that you can find in Amazon, and they commit suicide to protect their colony. And here, Colobopsis, this is ants, and they excrete their internal fluid to kill intruder to their colony. And here, if you see this macrotermites, the termite found you can find in Africa, so they bite and they don't let the victim goes. And bees, they sting and they're die. They're gonna die. So since I mentioned like individual sacrifice, this happened when there is a combat in the colony, right? And we also do have we human being also do some wars, right? Battle. And we send young people to army and they take these battles against enemy. I mean social insects do this kind of battle as well. And which soldier should go to the front line if a colony of termites gets attacked by the enemy? Young or old one? Can you type what you think? Should termites send their young soldiers to the front line or old soldier to the front line? Okay, Barbara, since you said old ones, can you unmute yourself and explain why you think old one?
Well, I've got grandchildren. I'd rather they live and I go.
Oh, that's nice answer. And Jen Stanley, can you unmute and explain why you think old one?
Because they're willing to give them up.
Hmm. So why? Termites send their old soldiers to the front line because the old soldiers have lower expected life. So their life expectancy is much shorter than younger one. So a Japanese termite research group demonstrate this phenomena in the laboratory setting. So they put one old soldiers and one young soldiers in this observation observational arena, and they introduce predator ants. And most of time, old soldiers show up to this kind of gates and they defend for their colony. But young soldiers stay near the king and queen and they stay behind. And this is a great example. And about like 10 years ago, one of my colleagues observed a fascinating behavior in French Guyana that a termite blew itself when they faced with danger. So here's video. Do you guys see the video playing?
Not yet.
No.
Not yet. Do you see them?
Yes.
Okay. So these termites, they're kind of explode by themselves. And this is very sticky. So if any insect that touch upon this fluid, they got stuck and they can't move. So this was on videotape to show the process of explosion. So we call this is explosive backpacks. My colleague investigated why a termite develop this kind of toxic chemical in their back. So in young workers, they are kind of new and their mandible is pretty sharp, like here, the B. But termites feed on wood material, and over time, their mandible become like dull. So if termites get older, they have lower wood consumption of they have less wood consumption ability. So they are not useless, but they develop a toxic chemical for their colony for the sake of their colony. And then when they encounter any opponents or predator, they commit suicide by exploding their chemical and they protect their colony. And another interesting fact of social insect is that they display alarm behavior. So many solitary insects, when they face danger, they just leave. So when you try to catch, when you try to kill mosquito or any flying moths, they just fly away, right? But in social insects, when an individual encounter any danger, they produce alarm signal to to spread out to tell their friends and family to to protect by themselves. So this is kind of optimized survival and it minimize losses. So even though this single individual lost their life, lost its life, the other colony member will be safe. And another interesting biology of social insect is they are pretty good builders. So this is a nest of a macrotermites that you can find in Africa. And this is Formica ants nest. And they have this kind of beautiful nest. And they build by themselves. So a friend of mine, he went to Australia and his height is about 6 feet. And this is a termite mound. And this gigantic mound you can find everywhere in Australia. And ants, in case of ants, you probably have seen this kind of ants opening in your yard or in your garden. And underneath of its ants opening, you can find this cool ant nest. All the chambers are connected, and this ants build, construct this kind of nest underground. So sometimes you can find this gigantic termite mound as well in Africa. And sometimes elephants used to wipe out their ass after pooping. So and sometimes social insects also create a arboreal nest, like this kind of ball shape in trees. So now I will move to a collective behavior. This is my favorite topics, and And I'm not sure if you have seen this kind of if you have seen this army ants living bridge. So when army ants forage for food and there is some like gaps they cannot cross, individual form a bridge and the other like ants can cross over and bring food back to the nest. So social insects such as ants and termites exhibit collective behavior where individuals interact and coordinate their actions to achieve complex tasks that benefit the colony, such as foraging, nest building, and defense. And interestingly, this behavior arises from local interactions, meaning that there is no centralized um, messenger, like queen or king do not say anything for ants or termite to build these kind of structures. So recently, so some people ask me like, do social insects perform like better job than human in like problem solving? So recently, a research group in Israel did a wonderful experiment, and I want to share with you. Oop, there we go. Oh, Isn't this cool? Oh, so peg termites are truly everywhere in Australia are renowned for their ability to combine individuals to achieve a goal for all. In Australia, they develop a metal cap with sharp bent down edge to place on top of the foundation. Yes, that's termite mesh. But to prevent termite, I have seen a window sill that appear to be solid, disintegrate into dust vent. Yeah, that's true. I mean, in Australia, people use metal sheets to prevent termites. Looking for ants or yeah. So and and so I will give you another example of like social insect behavior that how they navigate from one route to the other. Like I have to confess that I'm really bad at finding a route without Google Map. But social insects are really good at finding a food source and transport back to their colony. So if you look at this video, this is what I did in my PhD, and this is where termites come from. And they excavate this soil to find food resources. And they do this kind of work. And yeah, they find food source. So I was very interested in how termites find a food resources and if they have an ability to find shortcuts. So let me ask you, I'm pretty sure everybody in this Zoom meeting have been to Vacaville outlets, right? So can anyone tell me the shortest way from In-N-Out Burger to Walmart? You can unmute yourself and explain how to get from In-N-Out Burger to Walmart. Nope, nobody knows how to get from In-N-Out Burger to Walmart.
You can go out of In-N-Out Burger, make a right onto Nut Tree Parkway, and then make a left at the light at Helen Power and just drive down Helen Power and make your left into Walmart.
Oh, cool. Yeah, I think that's the right answer. So the shortest pathway from In-N-Out Burger to Walmart is what Michelle explained. But the problem of, so we call this process as path integration. So navigation system to track distance and the direction. And so that once social insects have this path integration, they can return quickly without losing their way. So, but like many social insects, like the example is subterranean termite here. So they have nest underground and they excavate tunnel like I show here. So they excavate tunnel, but they don't know where the food are. They know where they start, but they don't know where the destination is. So for example, in termite case, in the viewpoint of termite, they know they are In-N-Out Burger, but they don't know where the Walmart is. But they can find a shortcut. I will explain how they can achieve this. So path integration is always performed by finding shortcuts or finding shortcut by individuals trying, and eventually this path integration and finding shortcuts improve their foraging efficiency. So, for example, termites form underground nest and they start foraging by excavating tunnel like this. So there are many different ways to get to the food source. So if this is home, oh, and if this is nest, this is food, sorry. Oh, oh. Do you guys see my drawing?
It's pretty hard.
Pretty hard.
Okay.
Okay.
Yeah, we can see it, but it's pretty, you have to look
Okay.
carefully.
Okay, so on your left side is a food source, and on your right side is a colony, is their home. So if you look at this tunnel, termite can pick many different routes to get to the food source. Do you understand what I'm saying? So again, on your right side is termite home of termites. And on your left side is a food source. And there are many different ways to get to the food source from home, you know? So my question was how termite can find a shortcut. Oh, let me remove this. Okay. So so my hypothesis is that termite will randomly excavate their underground tunnels, and once they discover food resources, now they can find shortcut to transport their food item to their home. And my hypothesis is that there is a trade-off between food searching and food transportation. If termite excavate tunnel randomly underground, they may increase the chance of food encounter, but that probably give a lot of burden to termite. But once they find once they find food resources, they can transport their food item to their nest by creating a shortcut. So this is an example and what we talk about in Vacaville outlet mall, that if I know where I am and if I know where I go, you can probably think of your route, right? But as I said, in termite case, they know where they are, but they don't know where the destination is, and they have no idea about the pathway. So if you look at termite closely, sometimes they construct this underground tunnel and they don't find these food resources. And this is like 1 millimeter, just like thickness of credit card, and they missed. So I did a fun experiment by providing these 3 different shapes of tunnel structures, and I introduced termite and see how they create a shortcut. It's a good question, Barbara. So how do they navigate? John, yeah, that's true. I don't want they find a shortcut to your house. Barbara's question is, how do they navigate underground? How do they have directional capability? So we think termites find a water source, water like moist environment. So they try to like excavate tunnel toward the moisture source. So in underground, termite excavate tunnel just randomly. So if they do random excavation and it like over time, they will eventually find something that they can feed on. So I will explain that later. So I provide three different shapes of experimental arena. So the first arena I call straight. I introduce termite from here, and there is straight line to the food source. And I was wondering if they excavate another tunnel. And next arena, I turned detour. So I provide a route like this, and I want to observe if termite can excavate this shortcut from introduction point to the food source. And I gave termite another challenge that I named it detour and twisting. So termite was introduced from here, and they had this kind of twisting and the food source. And I also wanted to see if termite can find a shortcut. So yeah, so this is how it looks like. When they have these straight tunnels, they don't excavate many like different tunnels to find any other food resources. But if they have this a detour tunnels toward the food source, eventually termite excavate a shortcut from the entry point to the food source. And more interestingly, if we look at detour plus twisting, termite first create a shortcut to bypass twisting area. And then they start creating another shortcut from entry point to the food source. So this is an example of collective behavior in termites. And termite achieve this without any centralized information. Termite just react against the local environmental cue. And this is just an example that at the beginning, termite excavate less tunnel in straight arena, but in detour and detour plus twisting arena, they excavate a lot of different tunnels. And over time, their foraging distance from entry point to the food source, in the straight arena, their travel distance remains same. But in detour and detour plus twisting arena, their travel distance significantly decreased over time. And they found this shortcut in 24 hours. So once termite found a shortcut, they display another interesting behavior. So once they have this shortcut, it's much shorter distance to travel, right? So when they created this shortcut, every termite just used this shortcut. So now termites widen this shortcut, you know. So let's imagine I-80 from Vacaville to San Francisco. Because the traffic is so dense and high, we have this like a wide highway I-80 near the San Francisco. But in Vallejo, near the Vallejo, the I-80 is just 3 lanes, right? So termite display this kind of widening of their pathway in response to their traffic density. And yeah, I mean, this is process how the pest integrated collective behavior occurs in termite. The first they find food source and they create shortcuts, and more termites travel through the shortcut, and then termites widen their shortcut. So basically, this is an example that I show you. If there is a nest on your right side, and if there is a food source in your left side, not all tunnel will be widened, but these, I mean, the pathway in the middle in the pictures become wider and wider over time. Like this. I think I'm running out of time, and this is what I prepare. And yeah, I will take any question. Please type in your chat or mute yourself and ask me some questions. Peck asked me, is the communication or cooperation for tasks through chemical signal or physical antenna? Yes, you are very right. This is how termite or ants communicates. So in case of ants, when they find a food source, they put prey following pheromone on the ground. So the concentration or the density of prey following pheromone increases, so more ants can follow that signal. And yeah, I mean, they also do like physical like tactile communication, physical touching their antennae to communicate. Any other questions?
Yeah, Dr. Lee, I have a question about the puzzle the ants and the humans were trying to solve.
Mhm. Mhm.
I mean, one is why were the ants trying to do that? I mean, what was in it for them? I could see the humans were given a puzzle, but I mean, what was the motivation for the ants to try to solve
So
that?
in that experiment, the bridge, I mean the object was a food. So ants have to move that food to the nest.
Okay, I missed.
So
Okay.
sometimes they can catch a like cockroaches, which is much bigger than their body size.
Hmm.
And when they move these dead cockroaches from their collection site to the nest, there might be some obstacle along the way. So they try to solve this kind of problem altogether, you know.
Yeah. Well, and then sort of the same question Peggy had. I mean, were they communicating? Do you have evidence of that? How were they communicating? Because they clearly it didn't seem to be just random behavior.
So right now we understand ants use trait following pheromone and they do communicate, but we don't know the detail yet.
Yeah.
And I'm pretty sure that research team is working on it because they found such an fascinating behavior. And hopefully, like in 5 years or 4 years, we will see how ants communicate.
And then last question, do you know whether or not that experiment has been replicated, if you will, to, where the ants were competitive in solving the puzzle? I mean, have they done that a number of times?
No, the paper just came out, I think about a month ago or 2 months ago. So I believe many entomologists is replicating that in their own laboratory, but
Mhm.
I don't know. I don't know the answer yet.
Yeah. Okay. That was pretty fascinating. Thank you.
Kelly asked me, what would you say are the major research gap about eusocial species? Anything that would be really great to investigate, which hasn't been yet, that you are especially curious about? So that's really a good question. And yeah, we do have a lot of unknowns and gaps about eusocial species. The 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 biggest question we have right now is how a solitary insect achieve eusociality. So as I said, there are four eusocial insects: ants, bee, wasps, and termites. Ants, bee, wasps are evolved from wasps. Basically, they are social wasps. And termites evolved from cockroaches. So they have two different evolutionary pathway to achieve, to acquire your sociality. So many people thought the relationship between individuals are the driving force to achieve eusociality. What they mean is that in ant colony, queen produce eggs and brood. So the relationship between queen and brood, no, relationship between each brood is 0.75. But in termite, there is a king and queen. So the relationship between each individual is kind of 0.5. So the research group in ants, bee, and wasps believe their theory is the major driving force for eusocial evolution. But most of termite people disagree. So they're kind of like continuously fighting, and we don't have any conclusion yet. I don't know if we will have conclusion in the future, but yeah, we are fighting and we are studying, and hopefully in like 10 years or 20 years, we have solid answer how eusociality evolved in insects. Was it like too difficult to understand? Because this question alone is probably like 5 hours lectures.
You had a question, why do ants get into my flower pots? Is it a food source?
Yes. So I don't know what kind of ants you get in your flower pot, but ants need water to survive, and ants like plant sap. So that's why you are having ants in your flower pots. Any other question?
No, that was fascinating.
Yeah. Yeah.
I
Thank you,
hope you
Dr. Lee.
enjoy.
Just fascinating. Thank you
Yeah,
so much.
Really appreciate it.
yeah, I definitely second and third that. That was fascinating. All right. So next week, Rose expert Mary Ellen McKenzie, who many of you have probably heard her talks before, and you know how passionate and knowledgeable she is about roses, is going to talk about rose gardening throughout the year. So just a general overview of what to do with your roses through the year. So